piston-cylinder device containing 2 kilograms of air operates as a heat engine. The cycle begins at 1 megapascal and 650 degrees Kelvin. The air receives heat from the surroundings at constant pressure. It then expands adiabatically according to PV to the K equals a constant. It then rejects heat at constant volume. It finally recompresses adiabatically according to PV to the K equals a constant. The maximum pressure in the cycle is 5 times the minimum pressure. The maximum temperature in the cycle is 800 Kelvin. Determine the work and heat transfer for each process, all in kilojoules. Recall that R bar, the universal gas constant, is 8.314 kilojoules per kilomole degree Kelvin, and also the ratio of specific heats K is constant at 1.37. So lots of information given here, and let's start by summarizing this information just to make sure we understand what's going on. First of all, we have a small piston cylinder device here. There are 2 kilograms of air, and this is operating as a heat engine. So remember, a heat engine receives energy from the surroundings and produces work. First state is given, 1 megapascal and 650 Kelvin. So we know state 1 certainly. And then the problem statement goes through a description of a series of processes. And remember, it's operating as a cycle, so this is going to go back to its original state. So 1 to 2 is described as constant pressure. Then 2 to 3 is described as adiabatic, and an equation is given for the path PV to the K is a constant. And remember, it's described as an expansion. The third process is heat rejection at constant volume. So V is constant. And heat rejected. And then finally, 4 back to 1. And remember, it's a cycle, so we need to get back to 1, is again adiabatic. So there's 2 adiabatic processes. And same equation describes this adiabatic process. And this is a compression. Other things we're told, the maximum temperature in the cycle. We don't know which state point that is just yet, but we'll find that out soon. Maximum temperature is 800 Kelvin, and the maximum pressure divided by the minimum pressure is 5. So we need to figure out what state points all of those things are referring to, but for now that's the information we were given. What were we asked to find? Well, as is typical of these cycle type problems, we are asked to find Q, heat transfer, and work for each process. And certainly, if we can do that, we can calculate anything else that we might want to know about this thing, such as the efficiency. Now, we weren't asked to get the efficiency of this heat engine, but certainly if we know Q and W for each process, we could have done that. So Q and W for each process. So we're going to be going around this cycle and finding Q and W. So our assumptions, we'll begin collecting assumptions. And leave some room there and begin our analysis. Now this is a very good example of a problem that did not ask us to do a PV diagram, but we are very well advised to do that. So the analysis is going to begin with a PV diagram. And this is especially critical to figure out what this pressure ratio of 5 means and what point is the maximum temperature, which we were also given. So we're starting at point 1. And again, that point is fixed. We know that's at 1 megapascal, 650 degrees C. First process is constant pressure. It says air receives heat from the surroundings at constant pressure. So that means this must be an expansion. Okay, so P, V coordinates, 1 over to 2 at constant pressure. Then an adiabatic expansion, and it's a polytropic process. PV to the K equals a constant, and it's an expansion, so it must go like that to 3. Third process is constant volume heat rejection, which means the pressure is going to drop, so we go straight down to 0.4. And then finally, this cycle is closed with another reversible adiabatic. So we go reversible adiabatic back up to 1. And the direction around here, which is typical for a heat engine, is clockwise. So there is net work done on the surroundings because there's area inside of this, traced out by a clockwise curve. And these two processes here are both described by PV to the K is a constant. Now remember that the pressure ratio was given as 5. So P1 and P2 are both the maximum pressure, and P4 is the minimum pressure. So P1 over P4 equals 5. The other thing we can see by looking at this is that 0.2 is the maximum temperature. Remember, this process going from 2 to 3 is steeper than a line of constant temperature because the polytropic index is greater than 1. It's 1.37. So the maximum temperature, if we were to draw a line at 800 degrees, goes right through 0.2. So that's 800 Kelvin. So T2 is 800 Kelvin. And that's important because we need to know what temperature or which of our 4 state points that given piece of information refers to. Now what we've been asked to do here is calculate work and heat transfer for each of these processes. But drawing the PV diagram has allowed us to figure out what this pressure ratio means and also what the maximum temperature, where that's going to occur. So now we're in a much better position to tackle each of these processes in turn. So we start off looking at the first one, and that's a reasonable place to start because we at least know 0.1 is fixed and we can work from there. So let's look at work from 1 to 2. So work from 1 to 2, this is a closed system, remember? So the work is the integral of PdV. This is total work, that's a capital W, but we can say, we can take the volume on the right-hand side of this expression and express it as a ratio of the mass and the specific volume. And the mass is constant, can come out of the integral. Pressure is constant, at least for the first process, constant pressure process, so that can come out of the integral. And we have integral from 1 to 2 of dV. Notice that's now a specific volume because I've got a mass out front. So this is mass P V2 minus V1. And as is common with ideal gases, we see we have a product of pressure and volume on the right-hand side here. I can just replace that with RT. And of course, R is constant. So pressure times the change in specific volume is the same as the ideal gas constant times the change in temperature. And again, we can only do that because this is an ideal gas. So we should be going back to our assumptions list here. We use the integral of PdV, so that means quasi-equilibrium process. And in fact, we're going to assume all of these are quasi-equilibrium, so I say quasi-equilibrium processes and ideal gas. So that's the first two assumptions that we've already made. Back to our analysis here. Think about what we know and what we don't know. The mass we know. These two temperatures we now know because we figured out what T2 was. The only thing we don't know here is the gas constant, but we were told that it was air and we were given the universal gas constant. So let's just pause here and get the gas constant. which is the universal gas constant, divided by the molecular weight. Universal gas constant 8.314, and that's kilojoules per kilomole degree Kelvin, divided by molecular weight of air, which is 28.97, and that is kilograms per kilomole. So that gives us the specific gas constant for air, 0.2870 kilojoules per kilogram degree Kelvin. So notice it's on a mass basis now. Now, while I'm working with the gas constant here, I'm going to use it and our knowledge of the ratio of specific heats to get a value for CV and CP, because I'm going to need those later on. So we know that CP minus CV equals R, and we're also told that the ratio of specific heats, CP over CV, is 1.37, which means that 1.37 CV, which is just another name for CP, minus CV must equal R. So we can solve for CV from that. CV comes out to 0.77568 kilojoules per kilogram degree Kelvin. And actually that's the only one of the specific heats I'm going to need later on, because we'll be calculating changes in internal energy with that. We don't need CP because we don't need to calculate changes in enthalpy. So we looked at that just to get the gas constant. Now we can go back to our work calculation from 1 to 2. So we know the mass, 2 kilograms. We now have our gas constant, 0.2870 kilojoules per kilogram Kelvin. And we have our temperature change, T2, 800 Kelvin, T1, 650. And both of those temperatures are in Kelvin. And we calculate that, and it works out to 86.096 kilojoules. So we found our first energy transfer here, and we'll just state it to 3 significant figures. So 86.1 kilojoules. So the work transfer from 1 to 2, 86.1 kilojoules. Now we move on to heat transfer, and because it's a closed system, we use Q minus W equals delta U. So U2 minus U1. Notice all uppercase. So that's the first law for closed systems. And in writing that down, I've really assumed that kinetic and potential energies are negligible. So I gotta go back and say kinetic energy and potential energy are negligible. So make sure we go back and fulfill that assumption list when we make any assumptions. Now we have everything that we need to do this, because we're going to let the change in internal energy on the right-hand side here be the mass times CV times T2 minus T1. So notice that I'm using constant specific heats here to calculate the change in internal energy. Now we were told in the problem that the ratio of specific heats, K, is constant at 1.37. Well, if the ratio is constant, then they must both be constant. So we can use CV delta T to get delta U. If we wanted to, we could go to ideal gas tables and look up these internal energies. That would be certainly acceptable. It would give slightly different answers, and in fact they would be a bit more accurate. But in the context of what we've been given in this problem, it's certainly good or allowable to assume constant specific heats. So in fact, we'll go back to our assumptions and just make that clear that that's what we've done. So I'm running out of room here, so I'm going to add this up here. So K is constant. And again, if you assume the ratio of specific heats is constant, that means the individual ones must be also. So we've got everything we need here. 2 kilograms is our mass. Our value is CV, is 0.77568 kilojoules per kilogram Kelvin. And our temperature change, same as before, 800 minus 650, and both in Kelvin. So that works out to 318.80 kilojoules. So just stating our final answer for that heat transfer to three significant figures, 319 kilojoules. So work and heat transfer for the first process is a matter of calculating the work directly from integral PdV and Q from the first law. Now we go to our second process, so 2 to 3. And the problem we have when we look at this process is we really don't know anything about point 3. We don't know the pressure, temperature, or the volume. So we're a little bit stumped for a while here because of the lack of knowledge about any properties at point 3. So point 3 is a mystery. Now the one thing we do know about point 3, however, is that its volume is the same as point 4. And this is where drawing the PV diagram can really help us out. We can look at that PV diagram for clues about information for point 3. So we need to set point 3 aside for a moment and look at the process from 1 to 4, because we know a lot more about it. We know the pressure ratio from 1 to 4. And we also know that the process from 1 to 4 is described by this polytropic equation. PV to the K is a constant. Now, at point 1, we know enough information to calculate the specific volume. So we can take the ideal gas law, rearrange it for specific volume, and we have everything we need to calculate this specific volume. So we put our gas constant, 0.2870 kilojoules per kilogram, our temperature, 650 Kelvin, and our pressure, 1,000 kilopascals. And all of that gives us a specific volume of 0.18655 meters cubed per kilogram. So we've got V1. So if we think about PV to the K as a constant from 1 to 4, we know everything except V4. So we can solve for V4. It will be V1, P1 over P4 to the 1 over K. And again, we know everything on the right-hand side. V1 we just got. And our pressure ratio is 5, and K is 1.37. So this gives us a volume at 4. And remember, the reason we're looking at this is that's also the volume at 3. So we go 0.60394 when we calculate that out. Meters cubed per kilogram. So therefore, V3 is the same number. So very important to look both directions from these points to get information about them. Well, while we're at point 4 here, the other thing we can get is the temperature, because that'll be later on, be handy later on. So T4, and again, this is just ideal gas law. We keep applying the same thing over and over again. So we know pressure 4, we know V4, and we know R. So this temperature works out to 420.86 Kelvin. Okay? All of that stuff is known. And we need to go back to this process from 2 to 3 because that's the one we're considering now. Well, that's also polytropic. So P2 V2 to the K is equal to P3 V3 to the K. So if we look at what we know and what we don't know in here, we know P2 is 1,000 kilojoules per kilogram. And we can get our V2 because we know all of the other properties there. So we'll set this aside for a moment and we'll get V2, and that's going to come from our T2 over P2. Again, we know everything on the right hand side there. I'll just fill this in here. So V2 is 0.287 kilojoules per kilogram. T2 is 800 Kelvin. P2 1000 kPa. So V2 is 0.22960 meters cubed per kilogram. Now we go back to our polytropic expression here, and we know everything in there except P3. So we're really starting to get some properties at point 3 that we can use. So P3 is P2, V2 over V3 to the K. And again, that allows us to calculate our P3. So 1000 kPa, ratio of these volumes, 0.22960 divided by 0.60394. And that's raised to the power 1.37. That pressure works out to 265.81 kilopascals. So P3 we know. Now we can get T3. So we're just applying polytropic process and ideal gas law. So T3, P3, V3 over R. Pressure, 265.81 kPa, which we just found. V3 is the 0.60394 meters cubed per kilogram. And the gas constant, 0.2870 kilojoules per kilogram Kelvin. All of that gives a T3 of 559.35 Kelvin. Now we're ready to take a look at this work because now we have enough properties at 2 and 3 to do the work calculation. So our work from 2 to 3 is the integral from 2 to 3 of P dV. So that's going to be mass P3V3 minus P2V2 all over 1 minus K. So that's the work for a polytropic process. And again, we can rewrite this because it takes a little bit less calculating as R T3 minus T2. We've already done the work of calculating these temperatures, so we best use them here. 1 minus K makes the work calculation a little bit easier. So we just need to put our numbers in here. 2 kilograms. Gas constant, 2870 kilojoules per kilogram. Temperature difference, 559.35 minus 800, both Kelvin, all over 1 minus 1.37. And working that out, 373.33 kilojoules. So the work from 2 to 3 is equal to 373 kilojoules. So direct calculation of work with polytropic process. Heat transfer from 2 to 3 is 0. Remember, it's an adiabatic process going from 2 to 3. So that heat transfer is 0. 3 to 4, the work from 3 to 4 is 0 because it's a constant volume process. The heat transfer from 3 to 4 we get from the first law. And by this time in the problem, we've done all the work to get these temperatures, so these calculations don't require too much additional effort. And again, use our constant specific heats here to make use of these temperatures that we calculated. So just substituting in the numbers here, mass 2 kilograms again. CV was our 0.77568 kilojoules per kilogram Kelvin for CV value. And our temperature change, 420.86 minus 559.35 Kelvin. That works out to negative 214.84 kilojoules. And remember, the signs are going to work out properly, so this means heat is being removed from 3 to 4. So Q from 3 to 4 is negative 215 kilojoules. Final process is from 4 to 1, and this is another adiabatic process described by a polytropic process. So we're going from 4 to 1. So that's going to be mass P1 V1, which remember is the final point, minus P4 V4, which is the initial point in this process, divided by 1 minus K. And again, replace PV with RT. And put in the numbers, 2 kilograms, 0.2870 for the gas constant. And our temperatures, 650 is the final temperature, and the initial temperature, 420.86. Both in Kelvin. 1 minus the ratio of specific heats, 1.37. And that works out to negative again. So work is negative because it's a compression, work being done on the system. Negative 355.48 kilojoules. So that to 3 significant figures is just 355 kilojoules. So that's the work for our final process. And then heat transfer for the final process is 0 because it's adiabatic.